Hello, everyone. Welcome to this presentation from Western Sydney University on gathering data to predict the future. Before we start, I just want to start with a acknowledgement of the country. With respect for Aboriginal cultural protocol and the recognition that its campuses occupy their traditional lands, Western Sydney University acknowledges the Darug, Eora, Darawal, which is also the Tatarawal, and the Wiradjuri peoples, and thanks them for their support of its work in their lands in Greater Western Sydney and beyond. So in this session, we're going to be covering the topic of gathering evidence to predict the future. And so this is focusing on data science. My name's Associate Professor Laurence Park. I'm the discipline leader for maths and data science at Western Sydney University. I want to remind everyone that this session is going to be recorded. Western Sydney University will record this Zoom webinar for publishing on its website. The presenter's audio and video, including the shared screen content, will be recorded. As attendees, your video and audio are not being transmitted, and you will not be visible or heard during the webinar. You will also not be recorded. Further to this, a recording of this webinar may be published online for reference. Attendees will not be visible or heard in this recording. Participation in chat, so question and answer or poll sections of the webinar, is completely optional. By participating in the chat, you consent to the information shared in these sections being collected and used by Western Sydney University for learning purposes and to build a catalogue of frequently asked questions for the benefit of other prospective students. All right, so I just want to start with welcoming everyone to this presentation. I'll first talk a bit about me. So I'm, like I said, Associate Professor Laurence Park. I'm the Director of Academic Programs for Data Science at Western Sydney University. I've been doing research in data science for about 20 years now. And I've been teaching in data science for around 10 years. My best bowling figures in cricket is 6 for 32, which was in the semi-final as well, which helped us get into the grand final, and we went on winning. So well done to me. And I've just got a link there below to my my personal page that contains information about projects that I'm doing, research that I've done, publications that I've had. And so if you want to know any more about me, you can look at that. So first, what is data science? I know that we hear about this topic a lot, and we often hear data science together with machine learning and artificial intelligence, and it's often mixed in together and difficult to understand exactly what each of those are. So in one sentence, data science is the science of converting data into information. So data is pretty much the things that we receive from measuring things or even recording things. And usually we want to use that to answer questions. So a data scientist's job is turning this data into the information that we can use to help answer the questions that we need. So this talks about predicting the future. And so I wanted to show how what we can do to predict future events and what data scientists do to do this. So what we do naturally is we learn from previous events. We record what's happened before, and we use that to help us to predict what's going to happen in the future. If we want to predict the outcome of a system, so any system, it could be a system of people making purchases, or it could be a system of whales traveling through the ocean, or a system of viruses, or anything that where interactions occur and things are produced from it, then we first need to understand how the system works, and also the inner workings of the system. If we were the controller of the system, we'd know exactly all the moving parts and what happens at each stage and what's going to happen next. So by collecting data, which we can also say that's evidence of the past events of the system, we can try to reveal how the system works. If we're just observing a system and we don't understand how it works, we can observe what happens and try and reverse engineer that and work out what's inside that system, how is it moving and how is it working together. And once we understand that, we can then use that to help us gain more knowledge about the system, and also make predictions from that. So what we do as a data scientist, we first assume a model of the system, so some type of mathematical model, and then from the data that we've gathered, we tune the model so that it best matches the system from what we've seen. So then it behaves like the system. A data scientist is able to provide an appropriate model, tune the model parameters, and then use the model to explore the system and provide accurate predictions. And also not only just the predictions, but also some type of confidence with the predictions on how accurate that prediction will be. I'm going to start with a brief history of data science. And so we're going to go back a fair bit. If we go back to the 8th century, we find that data analysis was used as early as that in order to try to decipher encrypted messages. So one way of working out codes is to, well, the simple codes is to simply build frequency tables of words and write down which words appear more often than others. Or you can even go even lower and do that with letters. And so once you receive an encrypted message, you can then observe the frequencies of each of those as well and match them up to try to decode the message. And so these methods were used back then, where people built tables, recorded tables of words, and recorded the statistics of each of them. So if we move along from there, the first known use of using data to answer questions, I suppose, was in around 1662 by John Grant. And this was with the bills of mortality. In London at that time, the bills of mortality were set up to record deaths from plagues that were happening. So plagues used to rise up every now and then. And so a lot of people would die, and a register was taken to record the deaths, and it later also record the births as well. And so people were sent out to record this information. They got payment from it too. And it turned out that the people who were sent to collect the information weren't the best people, and sometimes they would take advantage of this information and try to collect more payment than needed. Or I've even read that they tried to take things from the people who had died. And so John Grant was analyzing the data, and he found that a lot of a part of the recordings of this data about the types of death from the different plagues that were around weren't as accurate as thought. If we move on to 1724, we find Abraham de Moivre, who was able to look at the records as well that they had of births and deaths to predict how long a person would live. And so based on their lifestyle and where they lived and who they were. And this was used to predict how much that someone could pay in terms of interest over that time, and it ended up becoming, this methods that were used from then are still used by insurance companies today to determine the life's worth of someone, how much insurance to pay out if someone was to die. Moving along a few more years to 1786, William Playfair was one of the first to provide diagrams of data. So before this, tables were used, and so he created the bar plot and the bar plot and pie charts to present information. And this allowed people who weren't mathematically inclined to visualize the data. So we get into more the data science territory in 1801 when Gauss started tackling this work. Gauss was involved in many scientific ventures, and one of them was this modeling as well. One of the problems at the time was astronomers were tracking the what we call the dwarf planet now, Ceres, and it would travel behind the sun, and the astronomers wanted to know when it would come out and where it would be. So Gauss took the data of where this dwarf planet was as it passed behind the sun and was able to build a model of the planet and use the data to then predict where it would appear as it came out from the sun. So this was the first use of actually taking data, getting a model and fitting it to data to make predictions. A few years later, Legendre extended this work to make it more general to use for any model. And he invented the least squares curve fitting method. So this method was able to take some data and a mathematical model and then provide a best fit. And that's what we can see in this plot over here of the curve of the blue line and the green dots. So he designed the method for fitting that line. Data science doesn't only involve the analysis of numbers, we need machines to do this. Early computation was inspired by the problems in astronomy at the time, the analysis that needed to be done. And the first computational machine was designed in 1837 by Charles Babbage. He pretty much took this idea from looms at the time, which were used to weave fabrics, where they had an automated loom machine. And he designed the first computer. Ada Lovelace was the first person to write a computer program for this machine. And it turned out later that this machine wasn't built at the time due to the cost and time constraints. But it was built about, I think, 30 years ago for one of the London museums, and we can see the machine there. Florence Nightingale is one of the famous figures that you've probably heard of. She's known for being like the patron of nursing. She was also a data scientist as well. She visited camps during the Crimean War to record the deaths of the soldiers. And what she found was that the majority of soldiers were actually dying from the unhygienic practices in the camps. So people there were hospitals in the camps. People didn't wash their hands. Blood was kept everywhere. When people went to the toilet everywhere. And so if someone came to the hospital with an infection, they would usually leave worse off or even die from it because of the practices in the hospital. So from her work, people learnt to clean up and wash hands. And she was able to provide these really nice plots as well. So I can actually show you one of the plots she gave on her Wikipedia page here. So there's her picture there. Here it is. So this is one of the presentations she made to show the recordings that she had. So here it shows the number of deaths over the months, and the blue regions show the deaths due to the unhygienic practices. So she was a pioneer in statistical graphics, which meant that we can now convey statistical analysis to people who didn't have a background in stats by just visually showing this information. Francis Galton was an important figure who came up with the idea of correlation on how things can interact with each other, and also standard deviation and regression as well. So he also created the Galton board to show how interaction between many independent things leads to this bell-shaped distribution, this normal distribution. And I've got a video here that shows this too. So let's have a look at this.
The probability of going down, and then
so here, these balls are just being tipped into the system. There's little poles along the direction. The ball, as it bounces on the pole, it can bounce either left or right. As it gets the next layer, it can bounce left or right as well, until finally it falls to the bottom. But if all these decisions along each path lead to the ball falling into one of these channels. And what happens is we do this with many balls, because of the way that the independent decisions are formed, we get this bell-shaped distribution. And this has become one of the important contributions to data science in the past 100 years. So all this is, each time a ball hits one of those poles, it bounces either left or right with a 50-50 chance. And so the majority turn up in the middle, and there's a smaller amount on the side, and they form this interesting curve, this bell-shaped curve, which is later known as the normal distribution. All right, I want to just stop here now, and also let's have a look at how we can do this by rolling dice as well. So one of the interesting properties of dice is that, let's say, a six-sided dice. When we roll a dice, we can get an outcome of either 1, 2, 3, 4, 5, or 6, and they're all equally likely. When we roll two dice and add them together, the chance of each of the sum of numbers is no longer the same. There's a greater chance of getting a 7 just because there's more ways of getting a 7. If we roll three dice, the shape changes as well, and it keeps going. And if we add more dice. And so I'm going to switch over to here. So here I'm using a program called RStudio, which allows us to, it's a programming language, but it's also great for data science. I'm going to take a sample of a set of numbers. So I'll sample from 1 to 6, and my sample size will be 1, and I'm going to sample with a replacement. So with a replacement means that every time we get a number, we put it back in the bag. So it's just like rolling a dice. So that means I can get 1 multiple times if I need to. So we're only taking a sample of size 1. So the replacement's not really used. So there's we just rolled a dice, we got a 1. If we roll it again, then there's our next number. Then we got a 4. If we roll it again, we get a 5. So what I'm going to do, I want to repeat this 1,000 times, and we're going to look at the outcomes. So I'll do replicate this 1,000 times. Well, let's do it 10,000 times. We're going to roll a dice 10,000 times and look at the outcome. So it's just roll the dice 10,000 times. And now let's look at how many times each have occurred. So I'm going to plot a histogram of the outcomes. And we can see here that each of the outcomes has appeared pretty much equally. Some of them a little bit more than the others, some of them a bit less, but it's pretty much a flat line across the side here in this plot. So we can see the 1, 2, 3, 4, 5, or 6 going there the same. Now let's roll 2 dice. So to roll 2 dice, we can take a sample of 1 to 6 of size 2 and replace equals, we'll sample with a replacement. So we can it's possible to get the same number all at once. So there we can see I got a 2 and a 6, a 1 and a 1, a 6 and a 2, and I'm going to add them together. So we're rolling 2 dice and we're adding them together. So there's our outcome, 8, 9, 7. So now I'm going to do this, roll 2 dice and add them together. We're going to repeat this 10,000 times as well. So I'm going to replicate 10,000. And let's put this in Y. So it's done that. Now let's have a look at how many times each of it has occurred. So before it was a flat distribution because we could get 1, 2, 3, 4, 5, or 6. Pretty much, it's the same probability. Now that we're rolling 2 dice and adding them together, we can see that the middle number, the 7, has a much higher chance of occurring. And as we get away from 7, the chance drops down. So there's 6 and 8 have the next highest chance, and then 5 and 9, and then at the end, 2 and 12 have the lowest chance. So we can see by rolling 2 dice, the only way we can get 2 and 12 is by either getting a 1 and a 1 or a 6 and a 6. But to get a 7 on a dice, we can either get 1 or 6, 2 or 5, 3 or 4, 4 or 3, 5 or 2, and 6 or 1. So there's 6 different ways to get a 7. So the chance of getting that is greater. So now I'm going to change this and roll 3 dice instead and add them together. And we can see this. Here's the distribution again, the chance of getting each number. We can now see it's kind of curving up, looking like what came from that Galton board. I'm going to roll 4 dice and add them together. And it looks even more like it now. So what happens is, as we add more of these independent events, when we roll dice, the rolls don't affect each other. So we're rolling them and we're adding them together. If we add a whole set of independent things together, they form this bell curve shaped distribution. And this is one of the things we see a lot in nature, pretty much because we've got this whole set of independent events coming together, forming together, to show that a lot of them, when we add them together, all these events cancel out and give you the middle. There's some high and some low, but not as many as in the middle. So for the rest of the 1900s, there was a lot of stats done and a lot of advancements, but we won't go into that. Computers started to come around. And so this led to big advancements into what we could analyze. So it started with Alan Turing. If everyone's seen the Enigma movie, you would have heard about Alan Turing. He pretty much had the idea of this machine that could compute. And it also brought up the idea of artificial intelligence. Can we get computers to think? And so there's also, that brought up the idea of our intelligence. What does it mean to think? So from this, people started looking into, can we actually get a computer to act like a brain? And this started the research into artificial neural networks. And so neural networks are made up of little functions, which we call neurons. And I'll show you what I mean here. So this is the Wikipedia page. It's got some good diagrams. So here we can see this here. Each of these circles is part of a neural network. And in a neural network, we just take the circle as some function that has inputs and it has one output. And the inputs are all multiplied by something in order so that when the signals come in, the output is high for some combination of inputs and it's low for some other combination of inputs. So the problem is, how do we determine how to control the input? How do we control what comes in order to give high or low signals out? And that meant that it's a difficult problem, and that research into neural networks kind of stopped until the 1980s. And so in the 80s, the backpropagation algorithm was created and allowed us to actually train these neural networks on computers. So we could just provide the neural network with a set of questions and a set of answers, and it would learn in order to, when we give those questions, it will give those answers. These are all numeric as well. So then we could give it new questions and it would try to predict the answer from that as well. So since then, we've had other machine learning methods such as support vector machines, hierarchical clustering, decision trees, and neural networks. And it wasn't until around 2010 that GPU computing took off, which allowed us to do much more, provide us with heaps of processing power compared to before. And so this allowed us to venture into deep learning, where we had neural networks that had many, many layers in the networks. So before I showed you a network with a few layers, these have many layers, which means we can have lots of variables to fit, and they could then learn complicated things. All right, so now I'm going to go into the uses of data science. So data science is, we've been saying it's used for prediction. It's also used for analysis of systems. And so some of the categories of what we can do are classification, which means we can predict the class of something, like what type of flower is this? What type of ball is that? Is the weather good? You know, classifying something. We can cluster things into groups. Regression means predicting the outcome of something, like who will win this game? What's the weather going to be like tomorrow? Or how much should we pay for insurance? There's also transcription, which is taking something and converting it into another form of coding, such as changing speech into text or music into music notation. Machine translation allows us to change between two different things, like translating from one language to another automatically. Anomaly detection allows us to find things that are different. So in space, is there something that wasn't there before that we can detect? Synthesis and sampling allows us to actually create things. And there's also finding missing values from data, denoising, and also density estimation. So data science is used in many places. A typical duties of a data scientist is to first define a question, then design experiments to generate the data, collect the data as evidence for answering the question, design a suitable model to answer the question, fit the model to data, and then finally analyze the model. And model analysis can provide insight into the process that led to the generation of data. So we build this model, which is like we're trying to replicate this thing we're examining. So once we have the model, we can actually look at it and understand the processes that are going on, and then we can use it to make predictions. So data science has been used in sport. There was a story a few decades ago. Also, it's been made into a movie that is that popular called Moneyball, which is one of the first uses of sport, data science in mainstream sport, where one of the American baseball teams, they analyzed their players' abilities and they found holes where they could, the type of players that they needed. And they were able to go out and get the players that they needed to make their team better, rather than just having people in the team have a feeling for what they needed. They actually used data to find what they needed. Top level teams use this now, and they also use a lot of tracking on their players to examine their fitness and examine how well they're going and making sure they don't get injured as well. Data science is used in business. So businesses offer products or services, and so they rely on customers to take up the offers that they provide. Data scientists analyze the sales and customer data to provide insights into customer behavior and the effectiveness of their products and services. And data science is also used to analyze the effectiveness of advertising. So Google are one of the big data companies that we know of, and they're also an advertising company too. You'll see Google ads on many sites. And so Google are constantly trying to work out what we're doing, what we want, and so they can provide targeted ads toward us. So then we can click on the ads and then they'll get revenue from it. I've also got a picture here of the rewards cards that many shops have, like Woolworths and Coles, so that when you buy products, if you use your rewards card, they can associate those products to you and start to learn your behavior on what you're buying. Data science is also used in the environment. So sensors are placed around the environment to record details such as temperature, humidity, or UV levels, or CO2 levels, or anything that needs to be measured. When I was a PhD student, I remember one of my friends came in with a leaf wetness detector. He found it behind the shop that they were throwing it out. I don't know what you'd need a leaf wetness detector for, but it exists. So data scientists build models to take this data and then help us to answer questions about, is there any change happening, or what can we do to help? Data science is also used in controlled experiments. So such as greenhouses exist where environments are controlled and set up, like the temperature and the humidity, to examine what happens to the environment within the greenhouse, such as the effect on plants or the soil. Data science is used in astronomy. So astronomers now have automated telescopes that they can see deeper than we've seen before, so they can see further into space. Data coming from these telescopes will soon be too much to manually examine. So we're getting about 1 terabyte a week of data, and so soon we won't even be able to store this data. It'll be too much. Data scientists are developing models to automatically examine the images as they come in, which will then help the astronomers by flagging any important ones or interesting ones so they can then observe them, because it's impossible for astronomers to observe everything they see right now. Data science can also be used to identify properties of galaxies, such as their redshift, or which will help determine their distance from us. Data science is used in social science. Social scientists now have access to large online social networks, which includes the relationships between the people and also the content that the people put on the networks. Data science is used to model these relationships and identify social structures, analyze the networks. Analysis of the networks allows us to determine how information flows through the network. And so by examining this, we can determine who is in control of this network, or who has power, how messages get passed around, and also how things spread through the network. It's almost like examining epidemics as well. Analysis of text in social networking services allows us to get an indication of also the voice of the public. If we can work out what people are saying in social networks, it gives us an indication of what people want. And data science is using art. So one question which is difficult to answer is, what is beauty? So we know that's a subjective question, that each person has their own idea of what beauty is. But even if you have your own idea of what it is, it's very difficult for someone to explain what they think beauty is. You could easily look at something and say, I think that looks beautiful, but you wouldn't be able to tell someone else what your algorithm is for beauty. So now that we have these deep learning systems that can learn complex relationships, we can have a whole bunch of, let's say, images or things that, but if we focus on images of things that people think are beautiful and not beautiful, and the deep learning method can learn these things, which means then it will know what you think beauty is, even though we can't look into these systems and actually determine why it thinks it. They're able to tell us what and suggest other images as well, and they can create images too. So here's one from Deep Dream, which was a system that Google set up, where this image, all it learnt was dog pictures. And then after that, the image of the Mona Lisa was provided to it. And since all it knew about was dog pictures, its image of the Mona Lisa could only be made up of these bits of dogs. And so we get these weird, freaky looking images like this. Data science can also be used to model the style of specific artists, allowing us to apply their style to other works. So this is another thing, style transfer, where we see the style of one particular artist being used on other people's work. And finally, data science is used in health and medicine. Health and medicine rely on experimentation to develop the effects of diet, lifestyle, and also medication. Data science is used to model the controlled experiments and observational studies to determine if treatments have an effect. So whenever a new drug's developed, there has to be experiments to see if it actually does what it's intended to do. And the data science methods help us with that. Data science models are also used in personal health devices, so such as Fitbits. So if you wear a Fitbit on your wrist, I know some of the models, all they do is detect your pulse. And so they're trying to determine the rest of your health purely from your pulse. And so these data science models are used to take that pulse and try to predict the rest of your health from that. All right, so now we've gone through the bit of the history of data science. We've explained where data science is used. Now we're going to go through some basic data science concepts, so we can actually see how these things work. So the simplest thing we can do is we can take a set of things and predict which one we're going to observe. So let's say so in this case, we're just starting off with a bag of numbers. Many models used in data science provide a prediction of its expected value. So remember, the expected value doesn't mean the exact value, but it means what we think the prediction will be, and it should be close to the prediction as well, in terms of the difference between the actual prediction and what was guessed. So let's say we have a bag containing the numbers 1, 2, 3, 4, 5. If I was to put my hand in the bag and draw one out, then we would ask the question, which number do you expect that I would draw out? And so you can see that it could be either 1, 2, 3, 4, or 5. But if I was to make a guess such that my guess, I want it to be closest to the answer, then my guess should be 3, shouldn't it? Because since the numbers could be any, 1, 2, 3, 4, or 5, if I pick a 1, then the numbers 4 and 5 are far away from 1. if I pick 5, then the numbers 1 and 2 are far away from 5. But if I pick 3, it's close to all the numbers, isn't it? It's central. So that if the person does happen to draw out a 3, that's good, I've got it right. But if they draw out a 2, then I've got it wrong, but I'm only wrong by a little bit. If they draw a 5, I've got it wrong, but I'm wrong by 2 as well. So it's a little bit more wrong. And so in this case, we want to provide the answer that minimizes the error. So what we do, we try to model the error. We try to model how wrong we would be. And then we design the model such that the prediction we make sure that we're wrong by the least amount. So if the error is 0, that's great. That means we've got it correct. But if the error isn't 0, it means we're only a little bit wrong. And that's the way we design the models. So we can also use extra information to improve the accuracy of our guesses, of our predictions. So here I've got five students from year 7, year 8, and year 9, and I've recorded their ages. And so if I was to take these 15 students and to just draw one of them randomly and predict their age, then all I could do, my best estimate would be to kind of pick the middle of all these numbers, wouldn't it? So they go from 12 to 16. So like the best guess might be 14 or 13 as the central number, like the average. If instead I was told that I've got a student here and they're in year 7, then that extra information of them being in year 7 will help me. It'll help me refine my prediction. Because I can see now in year 7, the ages here are only 12, or I've got 12, 13, 11, and 14. So that means I can pick a number of like 12 and a half. And that means my answer will be a lot more accurate than if I didn't have the knowledge that this person was in year 7. So by getting extra information about who the person is or what data we need, we're able to refine our predictions and get better predictions from that. Here's another example of using insurance claims. So here now we've got the latitude and longitude of a set of places and the amount of their claim. And so if we were just told the amount of their claim, then it'd be difficult to predict. If someone said, I made a claim, how much did I claim? That's difficult, isn't it? But I could just like find the middle of these numbers and that would be my best guess. But if I was instead told the position, the latitude and longitude, then if it's exactly the numbers here, I could look up the number that's on the table. But if it's not one of these numbers, I could find the closest position. So suddenly I've got this spatial information, haven't I? The latitude and longitude are these are all places around Sydney. And so if I had a new claim, I could find which one's closest to the data that I know. And that would help me to estimate the claim. So once we know this extra information, we can refine our predictions. And that's pretty much what we do in data science. We gather the evidence, we find out what do we know. And then once we have what we know, we can use that to make better estimates of what we want to know. So far, all these examples have been numeric. We've been giving numbers in and we've been getting numbers out. But I've talked about a lot of different other types of data, haven't I? I've talked about images. We've also said like videos and sound and social networks. So how do we use these different types of data when all we've shown so far is numbers? So for example, how do we locate traffic signs in images using these data science methods? How do we predict the style of a given piece of music? How do we predict if a tweet contains a racist statement? So each of these problems here, I've actually worked on in my own research. And all these types of data as well is data that we can record on a computer hard drive. If we look further into computer hard drives, all they're storing is ones and zeros, which are numbers. It's the combinations of ones and zeros that make up the data. And so anything that can be stored on a computer is actually already represented as a number. Now in data science, we mightn't use that number that is stored on the computer, but we take the things and we map them into numbers that make them useful. So all the data is represented as numbers somehow. So as an example, an image is a grid of pixels. And each of those pixels is just an intensity value. So that you might have red, green, and blue as well. So that means we have an intensity of red, green, and blue. And those intensity values are just numbers. So really, an image is just a grid of numbers. A sound is a waveform. So it's a sequence of pressure levels. So you often see these sound waveforms. Now that waveform, we can just represent as the height of the wave. So that means a sound is just a sequence of numbers. Movies are just both sound and images together, aren't they? So a movie is a sequence of images and a sound connected to that. And we've said already that images and sound are just collections of numbers. Text, we can represent by counting how many times the words appear. So if we just have a table with all the words, and for any given piece of text, we just record how many times each of those words appeared, suddenly we've got this representation for that text. And for social networks are shown by nodes connected to each other. We can actually change that to an array, so a 2x2 grid, where the columns represent the set of objects and the rows represent the set of objects as well. And the element is set to 1 if they're connected. It's set to 0 if they're not connected. So we can also convert these networks to a set of numbers too. So here we're getting a little bit into the maths. What we find is that any model is just a function. So before we were talking about having knowledge of the person being in year 7 or having knowledge of the location of where the thing was. So that's our input to the function. We give that in and out gives the prediction. So any knowledge that we have, we pass that into our function, our model that we've set up. And so this function here, f, represents our model that we've built. And out of that comes our prediction. Any data science model, even neural networks, can be represented as this. If people think that neural networks are some magical system, all they are is just a big function, a big complicated function. You put something in, you get something out. So here we've got some simpler forms of functions. Here's the one to predict a student age from their grade, from the data that we used before. So we might have that the age is equal to something, we don't know what this is, times their grade plus something. So if you've ever looked at straight line plots in your class, you'll probably see this is the same as y equals mx plus c. So here, instead I've written these betas instead of m and c. So this is just a straight line model. To do insurance claims, we had the latitude and longitude, didn't we? So we can just add another term. Here we've got something times the latitude, something times the longitude, and then plus something. So when we gather the data and creating this model, all we're doing is we're estimating what these betas are. And once we know what these betas are, then we can start making predictions. We work out what these betas are by gathering data as our evidence. So I want to go back to, let's go back to our studio, and let's actually use this data here of the student grades to, let's fit one of those straight line models to this. So I'm going to copy this. Paste this here. And now this is all the wrong way. So in this program, we represent tables using what we call a data frame. So I'm just going to call this D, and I write data frame, and let's call the first one Y7 for year 7. And that's equal to 12, 13. So I have to put the columns in 12, 11, and 14. And then let's write Y8 for the year 8 column. So we've got 12, 14, 13, 15. So these are just the values for this second column that I've got here. And the last number is 12. And then the year 9 values were 13, 15, 15, 16, and 14. So now we've created this data frame. I've just stored it in D. Oop. And so there it is there. So now I've realized I have to actually change what this looks like. So what I want is the ages as one column and the grade as another column. So let me change this. So let's call this year. And I'm going to make them all, put them all in the year column, and then I'm going to make a grade column. So there's all the values for year. And so now we want, oh, sorry, that's the age, isn't it? Not the year. Age. Now year, the year of their school level. So we had 7, 7, 7, 7, 7, and then we had 8, 8, 8, 8, 8, and then we had 9, 9, 9, 9, 9. All right. So now let's look at this. So I've changed this. You can see that now we've got all the ages and the year that they're in. So we can plot this. Let's plot the year on the x-axis, and we'll plot the age on the y-axis. And so there we go. There's our plot there. Look, it's a nice straight line going up, isn't it? Now in this program, we can fit this function that we showed before by using this other function called lm. So we want to model the age, don't we? And we want to model it with respect to the year level. And the data is in the variable D. So now I've done that, I'm going to put the straight line from this over the top of the plot. There we go. There's our fitted straight line. We can look more into the model. So I'll print out the details of the model. So this here is the beta 1 value, the coefficient beta 1 that we had, and this is the beta 0 value. So we've taken that model. The model was age equals beta 1 times year plus beta 0, and we found that from this data, beta 1 is equal to 1.1, and beta 0 is equal to 4.6. And so we've taken our evidence and used that to fit our model, and we've come up with these values, which now lets us predict if we wanted to know what the age was for someone in a higher grade, we could put that in and get out the values as well, because we've set up this model. All right. Yeah, so this is the one we just did there. We found the values of beta 1 and beta 0 from the data. So now we can use those values. We can use that model to make predictions. So we just saw two models there. One had two coefficients. One had two things we had to find, beta 1, beta 0. And the other one, we needed to find three, beta 2, beta 1, and beta 0. And we find those using data. So some models that we set are simple like that and have only a few parameters, but we find that when we get to complicated models, they have many more parameters, and so we need more computation time to compute those. For example, one of the deep learning models called YOLO, which does image classification, it has 65,252,682 parameters. So that's a lot of parameters. So to actually find those parameters takes like a week of a computer running through images, trying to make sure it's getting the predictions right and slowly fine-tuning the parameters. So for this system, the input is actually images and the output is the prediction of the images of what's in there. So I've actually got this running. Let's have a look at this. So I'll start it up and we can have a look at this. This is just a function as well, remember. It's taking an image as the input now, And the output is the prediction of what's in the image. So I've started this. All right, here we go. So it's slowed down. Well, let me stop it flickering. It's slowed down because it's taking time to actually work out in each frame that I'm a person. I've got a glass here. Let me see if it's able to show that. Oh, there we go. It says it's a wine glass. I think this is just a normal glass. What else have I got? I've got a pen. Does it show that's a pen? It says it's a toothbrush. So it thinks my pen, I suppose it's a strange. Let's have a look at another pen. I think that, does it say pen? Oh, it thinks that's scissors. So it's doing its best. It's looking at things in the image, and it can actually, I've got a hat here. Does it detect a hat? There we go. I think it's a baseball glove. So it's using a fair amount of my processing power on my computer as well. It's splitting up the image, working out what's in there, and then trying to predict. So it's not only detecting what's in the image, it's also trying to predict what it's detecting. So this is something you can download from the web that other people have done and run yourself as well. All right, I'll just stop this. All right, so I'll move on to the conclusion. So we saw that data science is the science of converting data into information. Data science has a long history stemming from mathematics, statistics, and computer science. Data is used in many fields, and data science is used in many fields because of that. So wherever there is data, data science is used to take that data and convert it into information to help answer questions, to make use of the data. And data science can be used for prediction, analysis, and synthesis as well. So on top of that, since I'm the Director of Academic Programs at Western Sydney University for Data Science, I want to let you know about these degrees that I've set up. So one is the Bachelor of Data Science, one is the Bachelor of Applied Data Science. The Bachelor of Data Science is a 3-year degree, like most degrees. So this degree is for people who want to become a data scientist. So you learn all the data science methods, you get all the computing and maths and databases as well. But we also have the Bachelor of Applied Data Science, which is a 1-year degree. And that's for people who want to use data science in their career. So with this degree, it's 1 year because it has to be taken in conjunction with another degree, another 3 or 4 year bachelor degree. So it's pretty much you building your own double degree. You do it 1 degree at Western Sydney University. And with that, you take 1 extra year to do the Bachelor of Applied Data Science. And in that, it covers the units there that you need for the modeling and machine learning and the projects as well. So in each of these degrees, the final unit is a project that you do working with a supervisor on building something or exploring something, and you get to show it to everyone at the end. So for more information about the degrees, visit the handbook at handbook@westernsydney.edu.au, and you can even find that link in the main page of the Western Sydney homepage as well. All right, so that's it from me. I hope I convinced you all how great data science is, and I hope it was a bit confusing as well. That's good, because it is confusing, and the more you do, the more you learn, and the more other people look at you and say, wow, how'd you do that? All right, so I'll finish it there. Thanks everyone for coming. I hope this was informative.